Welcome. I'm Dr. Morton, and this is Logic Design Chapter 8. We're going to cover a bunch of combinational devices in this lecture, and I think you'll find it very interesting. And this will cover Chapter 8 in the book. So let's get going. Okay, so the initial picture here shows some combinational devices that we're going to talk about. We're going to talk about read-only memories. We're going to talk about multiplexers or muxes. We're going to talk about an adder. We're going to talk about a decoder. And then we're also going to throw in the exclusive OR gate and talk about that a little bit more. We haven't talked about that too much. But we have mentioned the name earlier in the course. All right. So learning objectives, one should be able to describe 4 common combinational designs and their functions. One should be able to describe the function of an exclusive OR gate with 2 or 3 inputs. I want you to demonstrate how to implement a logic expression with a multiplexer or a read-only memory or a decoder. And we'll show you how to do that. And these always show up on the second test. So this is something that you need to learn, all 3 of these methods. And then it might even be on the final exam too. Then we'll construct outputs, how to construct the truth table for a 4-bit adder, which has 4 bits of A, 4 bits of B, and a carry in, and generates 4 outputs. So the independent variables are A, B, 4 bits of A, 4 bits of B, and a carry in, and the dependent variables are the carry out and 4 bits of sum. So that's got 9 inputs and 5 outputs, and it has 512 rows because there are 9 inputs, so that's 2 to the 9th, and that's 512. And we'll talk about how you would calculate the correct outputs for every row. All right, so I want you to understand that. Here's some glossary terms which you can hover over. And so it turns out that these key combinational devices we're going to cover right now in this lecture are incorporated in many devices that you're going to encounter. And so that's why we want to talk about them a little bit. First, we're going to talk about multiplexers. Now, let me just say, this is a 2 input to 1 output multiplexer with 1 control line. So it's a 2-to-1 mux. This is a digital multiplexer. There is such a thing as an analog multiplexer, and we use them typically in microprocessors to enable us to have a whole bunch of possible inputs for, say, our A to D converter or a comparator or maybe a touch sensor. And we can select which one we want to go to our actual conversion module, because in most of those cases we'll only have 1 comparator module or 1 A to D module or 1 touch sense calculation module, and we have to be able to switch between maybe 12 or 16 different inputs on our microprocessor that are connected to different pins and even some internal connections. And in order to do that, we need an analog multiplexer, which actually is like a switch that dials between, say, 12 different inputs and connects one of those to the output. In that case, we're transmitting not just a 0 or a 1, we're transmitting the actual voltage level on the wire that we're connecting. And so it varies over a continuous range. But our digital multiplexers, which is all we're really going to talk about in this course, we either input a 0 or 1 and we output a 0 or 1, and there's nothing in between. So these would not work to connect wires that weren't operating in a digital mode, where they just had values of 0 and 1. If you want to have some other value connected, you don't need a digital multiplexer, you need an analog multiplexer. All right, that said, let's look at the equation for this. Now, I've highlighted it here. F equals A prime I0, where A is the control line, so A prime would be the inverse of the control line, plus A, the control line, times I1. So if the control line is 0, A prime is 1, and we're selecting for I0. If the control line is 1, A prime is 0, so we're selecting for I1. And we'll connect whichever one of these is selected to F. And that's how a 2-to-1 mux works. A 4-to-1 is the same thing, except we have 2 control lines. And we see one of those here. All right, now, the characteristic equation for a 2-to-1 has a few more terms. Let's look at what the actual circuit would look like for one of these multiplexers. So I'm going to pop this on here. And let me switch over. Okay, so our actual circuit and I think I'm not quite on the paper here. That's because I banged this thing around all over the place. Maybe that's better. Not quite still. A little bit like that. Okay. And maybe this has to go up a little bit. That's probably part of it. Okay, now. Okay, that's, yeah. It's kind of okay. All right. Well, anyway, let's slide this down then. Okay, and then it's twisted, apparently. All right. Okay, here we go. So, so we take our 2-to-1 mux. We have two inputs, I0 and I1, and we have a control line A, and we have an output F. Now, in some uses, we would actually have a wire going over here, and we'd have a demultiplexer that would then give us two possible outputs, and we would maybe even connect the control lines. And so this input then, this would be the mux, and this would be the demux. And we would have I0 here and I1. So we'd only have to have the one wire, but we could select between two signals to transmit. And sometimes we'll do that with a funny clock and do it in such a way that we're sampling it, and we can, as long as we band limit these signals, we can easily push a number of signals through a single wire. And through a fiber optic cable, you can push even more than that. So we do a lot of multiplexing, demultiplexing. Like, for instance, in the cell phone. Your cell phone only has a little portion of the bandwidth on the cell tower, and many other cell phones are using the same frequencies at the same time. And there are two different ways they do this. They talk about code division multiplexing and time division multiplexing. TDM and CDM. But and mostly in the United States we use the code division. In Europe they use a lot of time TDM. Anyway, so that's kind of what multiplexers were kind of originally designed for, but actually we use them for a lot of other things now. Now we put them in field programmable gate arrays, and in the field programmable gate arrays they actually are used to implement functions, and we're going to show you how to do that. So let's say we have a 4-to-1 mux. All right, so here's our little mux. Hopefully I'll get it on the table. 1, 2, 3, 4. I0 through I3, and we'll do I2 and I1 and I2. And we have an output F, and we have two control lines, A and B. Now notice, once you get more than one control line, they're hierarchical. So A is 0 for I0 and I1, and it's 1 for I2 and I3. B is 0 for I0 and I2, and 1 for I1 and I3. So you have to have them connected correctly to get things connected correctly. So remember, they're hierarchical. They're not interchangeable. Okay, did we see this? No. There we go. Okay, something like that. Okay. And I don't know why that's screwed up. Okay. All right, that's a little better. All right. So now, yeah. All right, so now we can write the equation for this. We already looked at this. We see that F equals A prime, B prime, I0. So when they're both 0, we're selecting for I0. Or A prime, B for I1. So when it's 0, 1, we're selecting for I1. Or when it's A, B prime, we're selecting for I2. And when it's A, B, we're selecting for I3. So that's the equation. Now, how are we going to use this ROM to implement any 3-variable logic function? Okay, pretty cool that we can do this. 3-variable logic function, and we can implement it with this little sucker. So the first thing we do is we get our 3-variable logic function in our truth table. So we'll do that. So we have A, B, C, and our output F. See if we're still on the page. That's good. Now we're going to populate all the things. One of the things we do when we are going to implement a truth table with a mux, we group the rows in groups of pairs, 2 rows to a pair. So this is be 0, 0, 0, 0, 1, 1, 1, 1. This is 0, 0, 1, 1, 0, 0, 1, 1, and finally 0, 1, 0, 1, 0, 1, 0, 1. Now let's pick a logic function. Let's say we're going to do f equals, I'll put it in shorthand notation, the sum of the minterms. There's 3 variables, a, b, c, so we'll put these down here. So f of a, b, c equals the sum of the minterms, 0, 1, we'll skip 2, 3, we'll do, so 0, 1, we'll skip 2, 3, we'll do 5, and we'll do 6. So 0, 1, 5, 6. All right. So let's write those in. So a 1 for 0, a 1 for 1, 0s for 2 and 3, a 0 for 4, and a 1 for 5, a 1 for 6, and a 0 for 7. All right. Now, the way we connect this, the first thing we'll do is we're going to connect the a variable to the hierarchical line, the a control line on the mux, and the b variable to the b line. And that takes care of our two higher order independent variables, a and b. But what about c, and how do we get the correct value for f? We've only got 4 wires here. Now we have to connect something to these wires to make this work. Well, if you'll notice, each pair of row corresponds to a value of a and b. The first pair, a and b, are both 0, which selects for I0. So I'm just going to write I0 out here. And then the next selects for I1, the next for I2, and the next for I3. Now we haven't brought C into bear here, but in this case, the value for F for this first pair of rows doesn't depend on C, if you'll notice, because it's 1 for both rows. So in this case, we can just set I0 equal to the voltage we're operating our device at, and we'll call this VDD, or you could call it 5 volts if we're using 5-volt logic, or you could just say it equals 1 or true, whatever. Now I1, notice these pair of rows don't depend on, the output for F here doesn't depend on C either, because it's 0 in both cases. So we can actually say this is just ground, or 0 volts, or 0, or false. Okay, so that takes care of the first 2 rows. But look at this pair of this pair of the first 4 rows. Look at this pair of rows. For row 4, the desired output for F was a 0, but for row 5, the desired output for F was a 1. So now we have a little problem. We can't connect it to VDD and have both rows put out 1s, because that would be wrong. We can't connect it to ground and have both rows put out 0s, because that would be wrong for the row 5. So what do we do? Well, it turns out if you look, notice that the variable C exactly follows the pattern for F. So all we have to do is just put I2 equal to C, which means it's 0 for the top row and it's 1 for the bottom row, because C will be 1 for this bottom row for 5, but for 4 it'll be a 0. Okay, so that takes care of that. What about for I3? Well, for the top row in this pair, F is a 1, and for the bottom it's a 0, which unfortunately is just the opposite of C. So that's a problem. Any idea? What might you do? Well, remember the inverse. What if you set this equal to C prime? Now, when C is 0, we'll have a C prime, which is a 1, going into I3, so we'll get a 1. And when C is 1, C prime will be a 0, coming into I3 and going out for F. and that'll be 1, 0 in that order. So that's how we do it. We have 4 possibilities. We have 1, the constant 1, the constant 0, C, or C prime. And it works exactly the same way with a 4 variable, with a 8 to, so this is a 3 to 1 mux, this is a 4 to 1 mux. With an 8 to 1 mux, we have 3 control lines for ABC, and then we use the variable D, so we use 1, 0, D or D prime for each pair of rows, and instead of 4 pair of rows, we have 8 wires, so we'll have 8 rows, 8 pairs of rows, 16 altogether. And so we can implement any 4 variable problem with a with an 8 to 1 mux. Right. Okay. So hopefully that makes sense. Okay. So all right. So that takes care of the mux, and I'm not going to spend a lot more time on this. I want you to I want to get to the ROM. And we're already 16 minutes in, so I'm going to try and get through this. Okay, so there's a lot to be said about ROMs. It's a pretty extensive topic. For starters, there are many, many different types of read-only memories. We could look at a ROM like this. So this looks very complicated. We have A, B, C, and D as our 4 independent variables. And we have F0, F1, F2, F3, F4, F5, F6, and F7. So we have 8 output functions. So that's actually a byte. So so with 4 variables, we have 16 rows. So we have 16 8-bit bytes that we can store in this ROM. So let me draw a little picture and kind of talk about this. I think it'll make more sense. So a ROM is basically like a big table. And so you can think of it like this. In this case, let's say we have 8 columns. I'm not drawing these very accurately. I'm having a bit of a problem here. 1, 2, 3, 4, 5, 6, 7, and we need one more, and I didn't leave enough room for that. Okay, and then we have a whole bunch of rows. So I'm going to do this. I should have made it smaller, I guess. And then we have to divide each of these up. And then we have this top row, which I kind of left for labels, but in a ROM, of course, you don't have any internal labels. All right, so what we can do is we can put, in any one of these locations, we can put a 1 or a 0, whatever we want. And so our binary bits here can encode information. And if we have 8 columns, we can put a byte in each row. Now we also have some outputs. In this case, we have 8 outputs because we have 8 bits per row, and we can output an entire byte in 8 bits. Now we also have some address lines, and we'll call these address lines. Maybe there's only one D. Address, ADRESS, yeah, address lines. And in this case, we have 4 of them. And the 4 address lines can code for 16 different rows. All right, the first row would be coded 0, 0, 0, 0. And we usually have these A3, A2, A1, and A0 for address 0, 1, 2, and 3. A3 is going to be the high order address line, and A0 is going to be the low order, and 1 and 2 are in between. These are hierarchically arranged. So you have to get this right to get the right row. So if they're all zeros, you're going to address this row, and what that means is that row is going to come out of the 8 outputs. Now, you usually also have something called an output enable, and it's usually active low, so we put a bar over it. I promised I wouldn't use bars, but that's another way to represent the inverse. So I guess what we should do for this course is put output enable with a tick on it. But on a data sheet, you'll always see it with a bar. Okay, so the address lines address one of the rows, and the data, as soon as the address lines address that row, if the output enable is active, which usually means it's 0, then the contents of that row, however many columns, in this case we had 8 bits, so the 8 bits come out, be 8 outputs. And the outputs are usually usually, sometimes they'll start with output 0, but frequently for some reason they start with output 1, 2, and so forth to output 8 in this case, but they might start with 0. And again, oftentimes you will see a byte. You usually do see, 8 bits, maybe 4 bits, maybe 16 bits, rarely 32 bits. Those are typically the values of the number of columns that they'll have. And you can have pretty big ROMs. The ones in the old days, we I think it was 2132 or something. Anyway, and it typically had 13 or 12 address lines, and it held 8 columns. It had 8 bytes. Now, let me just talk a little bit about how we think about ROMs. I want you to. This is the first time you're going to see this, but when you take Micro 1 and if you take DSD, you're definitely going to see this again. I'm going to talk about it because it's important to be able to decide to describe ROMs. Now, this is a ROM. You can see a little window here, and inside that window you can see the actual integrated circuit. And if we hold it up so you can magnify it a little bit, and we wiggle it around, you can even see the bonding wires that connect to the various pads. I don't know, it's hard to get it just right so you can see it, but it can be done. I could put it under the microscope. If you just kind of use your imagination, you can see the bonding wires, and you can see how it has like 2 rectangular areas where it's got very uniform transistors fabricated in the IC itself. Anyway, this was called an electronically programmable read-only memory that was erasable with UV light. So if you shined a nice bright UV light in that window for about 10 or 15 minutes, it would erase whatever was programmed, and then you could reprogram it. So this could be programmed multiple times. Now, in order not to have it get erased accidentally, you would normally put a sticker over this little window. And if you look in an older computer, and maybe even in the current computer, you'll typically find a pair of these ROMs, and I think this one actually is a. Let's see. Let me get on my glasses. I might be able to see it here. I think this is a 2716. So it was a standard ROM, and I believe I'd have to look it up. I forget. It definitely had 8-bit bytes, and I think it had I don't know. Not sure how many address lines. It was maybe 8K by 8 bits. Something like that. How do we size these things? Well, first off, we want to know how much data can it hold. And we usually talk about the word size. So for any given ROM, the word size is the number of output columns. So the one I showed you on the other sheet, it had 8 outputs. So the word size was a byte, or 8 bits if you want. And then the question is how many bits? The one we talked about, we had 16. So it could hold 16 times 8, or so what is that? So 4 times 32, 2 times 64, 128. So we're going to hold 128 bits. Now, sometimes they're rated in bits, sometimes in bytes, sometimes in 16-bit words, various things. But in any event, how much data can it hold? And that determines the number of columns, which is equal to the word size. In our case, it was 8 bits, or a byte for our word size. And then how many rows? In our case, we had 16. And then how many address lines? How many address lines? Well, we had 16 rows, so we had to have 4 address lines. So rows equaled 16. So we normally spec these things in terms of rows times columns. So this would have been 16 by 8, which then when you do the multiplication is 128 bits capacity. And then 4 address lines. Okay, so that's typically how we specify them. Now, I'm not going to go into any more detail. I will tell you that after the UV thing was a little bit of a pain because you had to unplug this from its socket and put it into the ultraviolet eraser to erase it. So normally, what we do now, we have electrically erasable, electrically programmable read-only members, and EEPROM comes in two varieties. Not related to size, but 2 varieties related to the way it's made. And the one variety is, we just call it EEPROM. And the other variety we call flash. And flash is what you have in your jump drive. If you have a jump drive in your pocket, it has flash EEPROM memory in it. We don't usually use the term EEPROM with flash, but it is a type of EEPROM. It's a little different than standard EEPROM because with flash, it's more dense, it's cheaper, it's easier to make, and the flash memory is, you can't erase a single location. You have to erase groups of locations, and it varies depending on how it's made. It might be a big group of maybe 128 bytes. It might be a small group of 4 bytes or 8 bytes or something like that. But it won't be just a single byte. It will be a group of bytes. And that's the big difference between the flash and the EEPROM. EEPROM has a little bit longer life. Flash definitely wears out, and if you use it many times, maybe 100,000 erases and reads and writes, you will wear it out. So all of your jump drives have special circuitry to try and evenly distribute the usage across the entire flash memory inside that jump drive. And that's the same thing with solid state drives, same thing. They're just flash memory, and it has the same kind of management software or hardware to make it work. Okay, so let me go back. Now, I'm not going to talk too much about this, but I want you to understand, how do you implement a function with a ROM? Well, it's actually very simple. If you have a 4-variable truth table, and this is your value for f, you just take the value for f and put it right in here. And if you have another function, you can just put it in F1. And depending on how many columns your ROM has, you can put as many output functions in it as you have columns. And you just connect your independent variables up to the address lines, making sure they're hierarchically correct. And then you just write whatever you want whatever is in your truth table, you just write it straight into your ROM, and you're done. It's very simple. You do have to make sure that you keep everything hierarchically. Now, these ROMs are electrically writable and electrically erasable, and you have some extra inputs to the chip to change the outputs into inputs and to actually do the writing. And sometimes it requires a slightly higher voltage to make that happen, and there's usually a programming power pin that you have to zap with a little higher voltage. In the old days, it used to be 21 volts for like 5 milliseconds or something, but it's nothing like that now. Now it's maybe 6 volts or 5.5 volts or something. You don't have to do. It's not, the requirements to program these things are pretty straightforward. Okay, let's go on. I want to talk now about a decoder. Here are some of the different types. There's mask ROM that's programmed at the factory. We still use this. If you were going to make if you needed a 100,000 ROMs with exactly the same context, and you're never going to change it, you would just get them factory programmed, and that would make them as cheap as possible. If you need to program them yourself, then you can get them maybe one-time programmable, like this one, or maybe you can electrically programmable, maybe ultraviolet erased, or electrically programmable, electric erased, or you can do flash programmable. So the exact type of ROM you use depends on a whole bunch of factors. We're not going to kind of get into that today. All right, and here's the same picture of that chip, and you can see the little bonding wires around the side and the same kind of looking die in here, and those bonding wires connect these actual pins. So this whole chip is quite big, but the actual integrated circuit's just that little piece in there. And this window's there to allow you to expose ultraviolet light and leach the charge that's been electrically jammed onto this floating gate back off. Okay, decoders. So here's a decoder. Decoders, in this case, it's a 3 to 8 decoder. So we have 3 control lines and we have 8 output lines. Now, the way this works is, and there's usually a trip enable line as well, so that you can, because if the chip's enabled, one of these outputs will always be high, depending on your 3 address lines. So if all 3 ABC are zeros, then you're going to have output 0 is going to be turned on, and if you want to have nothing, and all the others 1 through 7 will be turned off. If you want to have them all off, then you have to take the chip enable and disenable the chip so that none of these are active. Now, the truth is, and these other lines are they're probably zeros, unless your chip enable is off, and then they'd be floating, then they'd be essentially disconnected. Well, the chip enable becomes your data in, and this is how you could use this to demultiplex a signal coming over from a 8-to-1 multiplexer. And it can be used in that manner, but not always. You also have to, of course, send over the 3 control lines or have them generated at each end with some kind of very special synchronization, like using a satellite signal or something. All right. The way this works, you can actually implement any function, because all you have to do is pick up, let's say you have a function, let me write here. Let's say you have a little function. So you have a little function. Let's say you have f equals the sum of the minterms. Let's say 1, 3, 5, 7. All right. How would you implement this with this? And again, 3 variables, A, B, C. So how would you implement this? Well, easy. You take your 3 variables here and hook up your variables A, B, C, make sure they're hierarchically correct. And then you would pick, since we did 1, 3, 5, 7, you'd take output 1, output 3, output 5, and output 7. I have 6 shown here. And you put those to an external OR gate, and that generates F. So in order to implement a 3-variable function with this 3 to 8 decoder, you must have one external OR chip, OR gate with enough inputs to make this work. You don't connect any of the ones where F is 0. So if F is 0, say we didn't use minterm 0, so we just don't connect it. We didn't use minterm 2, 4, or 6, so we should leave those disconnected. But 1, 3, 5, and 7 should be connected, and that generates that function. So whatever minterms you need, you just connect those lines. And if you had a second OR gate, you could have another. You could have F0, F1, F2. All you need is another OR gate for each one, and just connect whichever minterms each function needs to have. All right, and then let's talk briefly about the exclusive OR gate. And I think I'll try and do the adder. We'll see if we have time. All right. So here is a 2-input exclusive OR gate. Notice that we have A and B and F. Maybe I'll switch to the I'll just write this out. Okay, let's say we have our exclusive OR gate. First of all, the symbol for an exclusive OR gate, and I think I covered this already briefly, has this extra bar up here. Looks like a regular OR gate with an extra bar. There's your output F. Let's say we have two inputs. All right, so the truth table with two inputs, A, B, and our output F. And that we write that A with plus with a circle around it for exclusive OR. All right, and we have 0. There should be 4. 0, 0, 1, 1, 0, 1, 0, 1. Okay, so if both inputs are 0, F is 0. If any of the inputs are 1, F is 1. But what do we do if they're both 1? This is where it differs from a regular OR gate. In this case, we output a 0. So a standard OR gate, if we make, say this will be G here, we'll call this G, this is OR, and this is XOR. So G would be 0, 1, 1, 1. If any output's a 1, we would have a 1. But for an exclusive OR gate, if two outputs are 1s, we get a 0. Now, what do you do for a 3 variable OR gate? Well, let's look at that. So here we do A, B, C, and our output F. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 0, 0, 1, 0, 1, 0, 1. All right, so I'll do them in pairs just for grins, no, not for any particular reason, just to keep them organized. All right, so if they're all 0, you get a 0. If you just have 1, you get a 1. Here's a 1, you get a 1. Oops, I have 2 here, so that's going to be a 0. I have 1 here, so that's a 1. I have 2 here, that's a 0. And here I have 2, that's a 0. What about when I have 1, 2, 3, all the inputs are 1s? For a 3 input, it's back to a 1. Which sounds a little screwy, because doesn't sound as exclusive as an exclusive OR gate. But that's how it's defined. So you just have to sort of memorize that. It's more like an even or odd gate, but there is such a thing as an even and odd gate, so I don't know. I'm confused about that. But in any event, this is an exclusive OR, and the exclusive, so that's the XOR, and the XNOR is exactly the opposite. So if we make another column, it's just going to be 1, 0, 0, 1, 0, 1, 1, 0. Okay, so it's just the inverse of the XOR. Just like the NAND is the inverse of the AND, the NOR is the inverse of the OR. But notice that the AND gate and the OR gate are not inverses of each other. Okay, one more thing. I want to talk about this adder, and I'm going to cover this fairly briefly. So here's what the symbol would look like for a 3 input. All right, and there are some interesting properties to it, but I'll leave you to read the book about that. Okay, and some logic design courses are based around the canonical forms of the exclusive OR gate only, and they don't do the AND OR. But oh, sorry, you can't see this. I didn't switch. Where's my thing? Okay, so anyway, here's the symbol. That's what it looks like. 3 inputs, the extra bar here, output F. And here's some interesting properties. You can just read through these in the book. But like I said, some logic design texts are actually built around the canonical exclusive OR gate. But it's not really how we do design for the most part. All right, I want to talk about an adder. So adders are super important. And so to talk about adders, the first thing we have to introduce is the 1-bit half adder and the 1-bit full adder. The difference between the half adder, the 1-bit half adder, and the 1-bit full adder is that the 1-bit half adder has an input A and an input B, but no carry in. And it has an output, it has a sum and a carry out. The 1-bit full adder has an input A, an input B, and a carry in. It also has then a 1-bit sum and a 1-bit carry out. So all these are 1 bits. All right, but I want to quickly look at the truth table for a full adder. And this is actually, well, this is the half adder. Let's look at the full adder, because this is really more interesting. So we have A, B, and carry in, and a carry out and a sum. Now, if you look at this, notice we have ones. They're not grouped real tightly, and as a result, the equations to describe these things are fairly complicated. Here's what the K-maps look like. Notice we can't combine any of these terms, and I left off a circle on this one. Can't believe I did that. So there are 4, so we wind up with 1, 2, 3, 4 3 variable terms. Yeah, I left off a circle. I got to fix that. And here we can group them, but we can only group them in pairs. There's no group of 4 that would really make this sweet. And this is the output function for the sum. So we have a sum here, and here's the output function for the carry out right here. And you can see this is going to be 3 2 variable terms, and this is going to be 4 variable terms. And I think I did that right? This is sum 1, 2, 3, 4. Yeah, 4 variable terms. Unbelievable, right? All right. So anyway, here are the equations. This is for sum, and this is for carry. 3 2 variable terms, 4 3 variable terms. And turns out you can't combine any of these. You can see that from the K-map. None of these boxes can be grouped. It's the worst possible arrangement. And what that does is that means all math is addition in the computer world. All math is addition. Subtraction is still addition because we use 2's complement and we just add. And if we multiply, we stack up partial products and add. If we divide, we basically subtract and compare. So all math is addition. And because of that, it's very impactful that these are complicated equations and not simpler. It has really made the hardware to implement adders, which again, that drives all math much more expensive than it would have been if somehow these had been nicer. All right. So what about a 4-bit adder? Oh, and here's what the circuit looks like for a full adder. 2 exclusive OR gates, 2 AND gates, and an OR gate. It's pretty complicated. It's not as trivial as we'd like it to be. And there's potential for a 3-gate delay going through this network. The way it's implemented here. It could be implemented differently and in a 2-layer, but the way it's typically implemented, we get 3 layers. All right. Here's a 4-bit adder. I'm going to cover this pretty quickly, but we'll spend more time on it later. We have 4 bits of A. We call them A3, A2, A1, and A0. We have 4 bits of B, B3, B1, or B3, B2, B1, B0, and we have 1 bit of carry in. For most simple addition, that's usually going to be a 0. But if we're doing subtraction, we invert one of these and add 1 by making the carry in a 1, and that does the 2's complement conversion. And all we have to do is throw some inverters in here and turn them on and off, and we can make it an adder or a subtractor. Here are 4 bits of sum and our 1 bit of carry out. So 4 bits of A plus 4 bits of B plus a carry in will always fit into 4 bits of sum and a carry out. Now, there are 9 inputs, 5 outputs. So that gives us a truth table with 2 to the 9th are 512 rows and 5 outputs for a 4-bit adder. And for a 4-bit adder. And how do you do this? Well, let's finish this up real quick. I'm just going to show you a couple of examples on the paper. All right, so let me get one more blank sheet of paper somewhere. Here we go. All right. So let's say we have our 4-bit adder. So I'm not gonna draw 512 rows. I'm just gonna do a few of them. Okay. So that way it's gonna make it a lot easier. And I typically do the same thing on a test, so that's why I'm showing you this. All right. So we have A3, A2, A1, A0, B3, B2, B1, B0, and a carry in. And then we have, for outputs, we're going to have a carry out and a sum 3, sum 2, sum 1, and sum 0. Now let's say I just arbitrarily pick some values here. Let's say I have 0, 0, 1, 0 for A, 1, 1, 0, 1 for B, and a 1 for a carry in. What values should I have over here? Well, it's easy. I just add the A, 0, 0, 1, 0, to the B, 1, 1, 0, 1, plus the carry in, 1, add these up, and that tells me what these bits should be. So 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0 and carry the 1. So this would be 1, 0, 0, 0, 0. It just came out that way. That's totally accidental. But anyway, that's what I got. And so our sum is 0 and our carry out is 1, which actually means this would be 1, 2, 4, 8, 16. So apparently that was 16. Let's see if that's right. So this is 2, and this is D. So that's 13, I think. Yeah, 13, and plus 1. So if we had 13 plus 2 plus, if we had 13 plus 2 plus 1, that would be 16, and that's exactly what that is, 16. All right, so so that's how this works, and we can do any row that we put in here by just doing this math and figure out what we should have here. And of course that's and then now think how difficult this is going to be. So in order to simplify this design, what we do, we don't have 9 independent variables and use that to do our design, because that would just be a huge mess. What we do instead is we take 1, 2, 3, 4 1-bit adders, and we daisy chain the carry outs, and so we have B3 and A3 in here, and sum 3 coming out, and a carry out here. We have a carry out and a carry in here. We have a carry in here and a carry out. We have a carry in and a carry out, and here we have a carry in. And here we have B2, A2 going in. Here we have B1, A1 going in. And here we have B0, A0 going in. And here we have sum 0 coming out, sum 1, and sum 2, sum 3, and here's our final carry out. So this is called design by iteration. Let me write that. So what we do is we take our 1-bit adder and we iterate it 3 times to get 4 of them, and that gives us a 4-bit adder. And it's a whole lot easier to do that design than to use a truth table with 512 rows and try and figure out how to simplify that. So that's it. I think with that I'm going to stop, and the next video, let me switch over here. The next video we will do chapter 9.